Hello everybody. Today I'm gonna talk about prediction and optimal feedback steering of probability density functions for safe automated driving. Let us consider a highway driving scenario and an ego vehicle whose perspective the events are seen. There are some cars on the left lane, let's say L1, L2, L3, and some on the right, R1 and R2, and also there is a vehicle ahead of the ego vehicle, let's call A. At a given time t0, the ego vehicle has some estimates about its own state, such as position and velocity, as well as the states of other vehicles. These estimates are not exact because of the measurement and initial condition uncertainties. These stochastic uncertainties later will be represented by joint state probability density functions or PDF. As we can see in the lower image, um, these estimates are time varying and the ego vehicle can predict the states of all the vehicles at any time during the time horizon t. In this paper, we present the time-varying stochastic uncertainties in the states of all the vehicles as time-varying joint PDFs. We have two main contributions. First, we propose a framework for non-parametric prediction of PDFs using characteristic ODEs. And the second contribution is performing feedback synthesis for the ego vehicle's stochastic states. We assume all the vehicles follow the kinematic bicycle model, which has four states: XY position, heading angle theta, and V, which is the velocity, and controls are acceleration and steering wheel angle. We also assume that each vehicle closes the loop with a nominal MPC. And at the beginning of the time horizon, the ego car will receive the data to estimate its own and the other vehicle's state. And with this information, it wants to predict where the state's PDFs would be in time t. Here is an overview of our work. With having the initial state PDFs for all the vehicles at time 0, the ego car predicts the joint state PDFs over the time horizon. Then we calculate XY marginal and use them to get collision probabilities and the safe target PDF. And then we design and apply the optimal feedback steering on ego vehicle to reach that target PDF. The joint state PDF of each vehicle satisfies this partial differential equation called Liouville PDE, which depends on the closed loop dynamic. And this is a first order PDE and can be solved using the method of characteristics. Capital N here is the number of samples. In this PDE gives a probability weighted scalar point cloud evolution, and we are not making any grids. We also do not approximate statistics or dynamics, and our nonlinearities are exact. And from the joint PDFs we obtain from the method of characteristic, we then compute the univariant and bivariant marginal PDF in XY coordinates. And here are some simulation results. In the left image, we have propagated Y marginals, and on the right, the X marginals over time for the same highway driving scenario that we introduced at the beginning of the presentation. In this scenario, if you remember, the ego car can either stay in its own lane or change lane. If it has to change lane, it must place itself in between two vehicles, but we need to know between which two vehicles is the safest. For that, we calculate the Wasserstein barycenter of the bivariate marginal, which is essentially a weighted average of PDFs of a pair of non-ego cars. Here, lambda 1 and lambda 2 are the weights, and for our case are equal. So we use this data to calculate the collision probability for each combination of the non-ego car, and it would tell us what is the safest option or what is the desired PDF for the ego car to be. Now, we need to design a controller to take the ego car from its initial joint PDF to the desired PDF at time t. Taking advantage of feedback linearizable structure of the dynamic, we can design our controller in the feedback linearized form. And here is our stochastic optimal control problem. Here we want to minimize the expected value of energy or U tilde over the entire horizon with respect to control joint state PDF subject to Liouville equation, satisfying the initial PDF as well as the desired PDF condition at final time. To help our calculation, we add a stochastic regulation or a stochastic noise to our system. And the stochastic optimal control problem takes this new form. As you can see here, our first condition has changed, and it actually turns out that this Hessian, which is a second order term, will make our problem numerically easier to solve. The solution of our problem, which is the optimal controlled PDF and also the optimal energy, can be obtained using function phi and phi hat, which follow these integral equations. And here kappa is the Markov kernel. And with the known kappa, in order to find phi and phi hat, which will basically gives us the our optimal solution, we need to solve this contractive fixed point recursion. At the end of this recursion, the converge value, phi0 and phi0 hat, will help us to find phi and phi hat at the previous slide, and basically we can find our optimal solution, which is the control PDF. Now, back to our driving scenario. According to the collision probability calculation that we did, a PDF in the middle of the upper image, the gray PDF, is our desired PDF, or basically the safest states PDF that the ego car wants to reach, which is between the car R1 and R2 in the right lane. And the lower image shows that by applying the optimal feedback control, the ego vehicle can reach that desired state. And here is the summary. We first calculated the time-varying non-predictive joint state PDFs for the all the vehicles in the highway. And then we compute the safest terminal PDF for the ego vehicle to be, and then we apply the feedback synthesis for the joint PDF steering for the ego vehicle to reach that desired PDF. Thanks.